Right, good morning. So, this is the final talk for me for this Gyan course. I really hope that you had a good time. So, this one is mostly applications. How we can use multiferroic composites for devices operating at very high frequencies. So, the unique thing about multiferroic devices that you can tune it with either an electric field or a magnetic field. So, tuning with the voltage makes possible to miniaturize all the devices that I am going to talk about. So, we all know what we have been discussing for the past 4 days is that there is strain mediated coupling between the ferromagnetic and ferroelectric phases in a composite. So, if you have a bulk composite, then the strain is rather internal within the sample. And for the case of a layered structure, then it is interface strain. So, now if you apply an electric field, there is piezoelectric strain, which would alter the properties of the magnetic field. This is the one we will be using for most of the applications for tunable ferrite devices. There is another option where we have a layered structure of a ferroelectric and a ferrite, and you can excite 2 types of resonances. One is ferromagnetic resonance in the ferrite and dielectric resonance in the ferroelectric. When they combine together in the frequency spectrum, you have what are called hybrid waves that can be tuned with either an electric field or a magnetic field. So, the advantage is the hybrid waves can be tuned over a wide frequency range compared to pure ferromagnetic resonance. So, we will discuss devices based on both ferromagnetic resonance as well as hybrid waves. Right. So, you are familiar with how we can study the nature of the converse magnetoelectric effect at ferromagnetic resonance, and also I will talk about how the hybrid magnetic dielectric modes behave under an electric field. Then for the device applications, I will discuss resonators, filters, phase shifters, delay line and attenuators. Miniature antennas we already discussed yesterday, so I won't be repeating that again. Right, you are familiar with this picture where we show a bilayer of a ferrite and a ferromagnet and a ferroelectric, and then you excite ferromagnetic resonance in the ferrite, then you apply an electric field, there is a shift in the resonance field. So, you estimate the shift in the resonance field as a function of the electric field. Then you draw a graph relating delta H to E, and the slope of that would be the coefficient of the converse magnetoelectric coupling, this term A. Now, we are going to discuss most of the devices based on yttrium and garnet. It's not highly magnetostrictive, but the advantage is it has very small line width and very low high frequency losses. So, it is a preferred material for most of the applications for devices operating up to 12 gigahertz. So, when you go higher in frequency, the problem is like for any YIG device, you have to have a biased magnetic field to operate. The higher the frequency, higher the field that you need. So, for 10 gigahertz, you need a field of 3 kilohertz. So, if it is 15 gigahertz, it is much higher. 5 or 6 kilo-Ørsted. So, the power requirement keeps going up and up as you go up in frequency. So, instead of using EEG at frequencies more than 12 gigahertz, what we prefer is either nickel ferrite or lithium ferrite. They are good up to 20 gigahertz. Then one can use hexagonal ferrite for 20 to 50, Y type or Z type and so on. For frequencies above 50 gigahertz, one has to use hexagonal ferrite with M type structure, either barium or strontium ferrite, and they are good up to 110 gigahertz. Okay. And for the composite, we are going to use either PCT or PMNPT. They have reasonably good piezoelectric constants. So, we did some theory, and the magnetoelectric coupling coefficient for converse magnetoelectric effect is given by the second term here. So, it is directly proportional to the product of the magnetostriction and the piezoelectric coefficient, and it is inversely proportional to the magnetization for the ferrite. So, these are some of the values of the important parameters for the ferrimagnetic oxides, and you are looking at yttrium and garnet. It can be you can have films with line width as small as 0.5 Ørsted. So, that is a key parameter, because when you tune a device, the question is what is the tuning range compared to the line width. So, if I can tune the device by several line widths, that is what we prefer. So, that is where the advantage of using EEG comes in. Nickel ferrite and lithium ferrite, they have a slightly higher line width compared to yttrium and garnet. So, lithium ferrite has about less than 10 Ørsted. It is rather difficult to get 2 Ørsted, that is the value mentioned here, but it is a challenge. And nickel ferrite has a much higher line width, even in the form of a single crystal film between 25 and 50. Nickel zinc ferrite also large line width, and Y type zinc to Y, it has a reasonably good line width, but these are all single crystal films. If it is polycrystalline, they are no good for device applications. The line width is too high, and it is not going to work. So, these are the magnetostriction around 100, 110, and 111, and looking at these numbers, the best values are for nickel ferrite. Lithium ferrite is also okay. The worst is yttrium and garnet. So, this one I showed in one of the earlier talks. It shows the FMR profiles, which is actually the derivative of the power absorbed by the samples under two conditions: no electric field, that is E equal to 0, then an electric field of 300 kilovolts per centimeter. And in each case, yttrium and garnet PCT, nickel ferrite PCT, and lithium ferrite PCT, there is a downward shift in the resonance profile. Then if you estimate from these profiles, these are theoretical simulation, and then you get these numbers here at the bottom for the shift in the resonance field. It is the smallest is for EEG PCT, that is 20 Ørsted. So, you can find the converse magnetoelectric coefficient for each and every case. For EEG, it is 20 divided by 300, it is rather small. For nickel ferrite, it is about 1 Ørsted centimeter per kilovolt, and it is little bit smaller for lithium ferrite, which is 75 over 300. that's 0.25 Oersted centimeter per kilovolt. So, in all these three cases, you can use the device at ferromagnetic resonance and then tune them with an electric field, if that's what you want to do. But the tuning is rather limited. And also you have to keep in mind that in each device you must have a bias magnetic field. So, the tuning in this case is small, but it is good enough if there is a device operating at room temperature and you want to make it operate over a wide changing in the temperature, maybe from 0 to 60 degrees, then the tuning that you can do with the voltage is enough to compensate for any shift in the temperature of the device. So, it is rather very limited capability, and we cannot tune the device over several operating bands. That is not going to be possible. Okay. So, as I mentioned earlier, depending on the frequency where you want to operate the device, you have to choose the appropriate ferromagnetic oxide, and 1 to 10, maybe 12 gigahertz, yttrium and garnet. These are usually deposited on gadolinium, gallium, garnet substrates, and the best technique for depositing these films on GGE would be liquid phase epitaxy. For single crystal Z and Y type ferrites, you can use LPE, but you may have to use other techniques such as pulsed laser deposition or chemical vapor deposition. And then barium and strontium ferrite, and also aluminum substituted barium and strontium ferrite. These single crystals, they are bulk single crystals. They are made by floating zone technique. I discussed this some time ago, where you have two halogen lamps, you heat a polycrystalline seed to about 1700 degrees Celsius, then there is a small sample of single crystal seed. So, once you start cooling the polycrystalline seed at very slow state, like 1 degree per minute, the cooling should be very slow for it to grow the single crystal. It is in the form of a cylinder, and then you can put together this kind of system to make a long rod of single crystal M type ferrite. Then it has to be annealed at very high temperature in oxygen atmosphere, because during the growth process you always tend to have iron 2+ in the ferrite, which you do not want, because if there are divalent iron in the crystal, that would make the sample more conductive electrically, and that will lead to losses when you use them in the device. So, the growth followed by annealing in oxygen at high temperature and high pressure of oxygen, it is a key ingredient when you make single crystal M type ferrites. And then we can form bilayers with PMNPT or PCT, and it has to be done by some kind of a bonding technique. It can be epoxy bonding, eutectic bonding, or silica bonding. In silica bonding, you can sputter a thin layer of glass, then heat it up at high temperature and apply some pressure between the ferroelectric and the ferrite, and that will lead to good bonding. But we tried all three of them. The best one and the easiest one is just the epoxy bonding. It works very well, and you do not need any fancy technique, but it is okay so long as you do not have any heating associated with the device. If the device heats up, then there is a danger of debonding the ferrite and the ferroelectric, and the device will not work anymore. So, this is the experiment where you look at the shift in the ferromagnetic resonance in an electric field and estimate the converse magnetoelectric coefficient. And this is one example that I showed earlier. It's on yttrium and garnet, and these are the first derivative of the power absorbed by the film. And as you apply an electric field and increase its magnitude, there is a shift in the resonance to the right. And here this graph shows the plot of shift in the resonance versus electric field, and the slope is the converse magnetoelectric coefficient that comes out to 5 Oersted centimeter per kilovolt. Okay, so this is the hybrid waves that I am talking about earlier. What we have here is a ferroelectric layer made of barium strontium titanate, that is BST. And BST has very high dielectric constant, and when you apply an electric field, you can tune the dielectric constant pretty well. So, that is a key ingredient in these hybrid wave devices, because the tuning involves varying the dielectric constant, and that is the reason we are using not barium titanate, but barium strontium titanate, and there is an yttrium and garnet film on a GGG substrate. They are bonded together, and the tuning voltage is applied across BST. These are the dimensions for the egg film and the BST platelet. So, what you see here is a magnetic mode in combination with dielectric resonance in BST, which is the hybrid mode that is represented by 1. So, as you increase the voltage across BST, the dielectric constant in BST changes. That leads to a large tuning capability for the hybrid mode, and you can tune it by about 25 megahertz for a voltage of around 1000 volts. That is very high, but that is what we did. And the Q value for the resonance is rather high, it is about 1000. So, but this tunability is much better than the previous one here, where you can tune it by 40 Oersted in an electric field of 8 kilovolt per centimeter. In frequency term, it is only about 100 megahertz. In this case, the tuning is 25 megahertz for a voltage of about 1000 volts. It is about comparable, but you can do a lot more with the hybrid waves, as I am going to discuss later. So, this is the electromagnetic frequency spectrum, and the range where the devices would operate is rather limited. 1 gigahertz is 10 power 9. So, we are talking about devices from 1 to 100 gigahertz. That is 10 power 9 to 10 power 11, and that is where it is a small region here, but that is where these devices are useful. Okay. So, the key parameters for the materials that are going to be used in the devices are high resistivity to reduce any losses, and also you need high magnetization and high Curie temperature. In case of heating, you do not want to have the device perform very poorly. So, that requires a much higher Curie temperature for the magnetic oxide films compared to its operating temperature. And you also preferably use films with low ferromagnetic resonance line width. So, the devices that you would like to put together. Depending on the frequency, these are the choices for the magnetic film. Yttrium and garnet, then up to 10 gigahertz. Spinel ferrites, both lithium and nickel ferrite, up to 15 gigahertz. Then the hexagonal ferrite, Y and Z type, the maximum limit is 30, and for M type, it's between 30 and 110. So these devices are used in phased radars, and they include resonators, filters, phase shifters, and so on. They are front-end elements in phased radars. And as I mentioned earlier, if you want to tune the operating frequency, then you generally use a variable magnetic field produced by a solenoid or an electromagnet that would make the device power hungry and also too big for any miniaturization. And also it can integrate them with any semiconductor devices. Okay. And also you have to deal with very large size and weight. So this is called swap: size, weight, and power. So the whole idea is to reduce the swap needed for these devices, and one of them is shown here, and it's a hybrid wave device with BST and YIG, and it's placed on this strip line. It can be used as a resonator or a filter, but it can be it's bonded to PZT and put it on this microstrip line, and then you excite it with microwave power. At ferromagnetic resonance, it will absorb the microwave power. So if you have an output arm, then this is a band stop filter where it will absorb power over a certain frequency range. So it can be used as a filter, but we'll get to it pretty soon. Okay. So before we came up with all these composites, people did some experiments and how to tune the YIG-based devices without varying the magnetic field. So these were published work in the late 1980s and early 90s, and this is a work from Ukraine where they used an YIG film on GGG, and they looked at the ferromagnetic resonance in the YIG film. Then they applied a mechanical force onto the film, and depending on whether the force is either tensile or compressive, they are able to tune the ferromagnetic resonance, and that's what is shown here. So in one sense, there was increase in the resonance field, and when it was compressive, the resonance field decreased. So they were able to demonstrate that you can tune it with a mechanical force. Why does it happen? If when you apply a force to it, it's like the magnetostriction, right? It would change the magnetic properties of the film. It can change either the magnetization or the anisotropy field. That would manifest as a change in the resonance frequency. So that's how they were able to demonstrate the tunability with a mechanical force. So we are doing essentially the same thing, except that the force is created by the piezoelectric strain in the composite. Okay? So I'll talk about these devices: resonators, bandpass filter, phase shifter, attenuators, and delay lines, and based on hybrid waves, resonators and phase shifters. Right. This is the ferromagnetic resonance in a polycrystalline multilayer of lithium ferrite and PZT. And look at this FMR profile. It has the line width. The line width is the separation between this dip and the peak. That's close to 800 Oersted. And even you have you apply very large electric field as shown here, the tuning is by a very small static magnetic field, right. It is practically nothing, it is just 8 yards stud. The line width is 800, it is a tenth of the line width. So, the tuning does not serve any purpose, right. So, the polycrystalline material is not something you want to use in any of the devices. It should be single crystal ferrites with reasonably small line width, so that the tuning is by several line widths. So, one of them is shown here. This is a resonator, and in this device the PZT platelet is bonded to zinc film on GGG substrate, and this is a strip line on an alumina ground plane. You place the film along with the PCT right onto the strip line, and you can apply a bias magnetic field either parallel to the plane or perpendicular to it. Then you excite with microwave power, and there is a vector network analyzer which is a source of microwave power, as well as it can measure the power reflected from the film or the transmitted power. So, what is shown here in the bottom profiles are the reflected power in this case as a function of frequency. So, the ferromagnetic resonance would show up as a sharp dip in the reflected power. That is because under ferromagnetic resonance, the sample, in this case zinc film, would absorb power. So, there is a dip in the profile. Then you apply a voltage across PCT, depending on the polarity of the electric field. There is a shift in the FMR profile to either higher or lower frequency. Then you plot the shift as a function of the applied electric field. So, in this case the PCT platelet is 0.5 millimeter thick. So, to create a field of about 10 kilovolt per centimeter, you have to use about 500 volts. Okay, that is pretty high, but it can be there may be difficulty applying that kind of a voltage in a practical device. So, the only option is to decrease the thickness of PCT. You do not have to use 0.5 millimeter thick PCT. Instead, you can decrease it to 0.1 millimeter, which is about 100 micron, and that would give you the same kind of electric field for 50 volts rather than 500 volts. Okay. And these data in the shift in the FMR are shown for two cases. One is the static magnetic field parallel to the plane, and the other is perpendicular to it. And when you change the polarity of the electric field, the strain switches from compressive to tensile, and so there is a downshift in one case, an upshift in the other case, and overall the shift in the ferromagnetic resonance is around 60 megahertz for electric field span of plus 10 to minus 10 kilovolts per centimeter. And all the devices they have a figure of merit. In this particular case, there are several factors. One is the quality factor for the resonance, that is Q factor. For the case of YEG, it is anywhere from 1000 to 5000, and the quality the number that would define the performance of the resonator is the ratio of the tunability divided by the line width for the YEG, that ranges from 30 to 120. And you can make a similar resonator with a ferroelectric. These are ferroelectric resonators, and you can tune them with an electric field. And if you put together a resonator with BST, that is barium strontium titanate, the Q values range from 110 to 100, and this figure of merit is 7 to 14. So, this device is, it has much better numbers, both Q and F, compared to ferroelectric only resonator. And okay, so this is the same device. What is shown here is the tuning over a very small electric field range, which is rather linear. So, you want linear response for tuning if at all possible, but if you want to have it, then the electric field range is rather limited. And looking at it, this is non-linear, it is not quite linear, but you can make it linear by working at a very small interval for the electric field. That is what is shown in this case. So, as you go to higher electric fields, it becomes non-linear, and also there is hysteresis certainly, and it gets worse if you go to fields on the order of 20 kilovolts per centimeter. Right, this is EEC, PM and PT. The earlier one was with PCT. It's similar behavior, except that the Q value for resonance is around 1000, which is same as what we saw for EEC PCT, and the tunability is 25 megahertz. So, it's not any better than what we got with PCT, but this is better in the sense that we are using here single crystal PM and PT, which is rather expensive compared to very cheap polycrystalline PCT. So, this case was where we used eutectic bonding to make the bilayer of EEG and PCT, and so the idea is to compare what happens when you use a bilayer which was formed with epoxy versus eutectic bonding, and we found that it is not any better than the epoxy bonding. So, why take all the pain to make the bilayer by eutectic bonding, and there is no reason to. And these are similar data for a sample of 1 micron thick nickel ferrite deposited on PM and PT or PC and PT by metallo-organic chemical vapor deposition. The deposition chamber is enclosed. There is a substrate of some material. It can be magnesium oxide or magnesium aluminate. Then you heat the substrate to about 600 degrees. Then you let the gas flow right on top of the substrate. So, the vapor has nickel in it, iron in it. So, it will deposit nickel ferrite at appropriate condition onto the substrate, and it is a very slow process. So, ultimately the thickness of the film is only 1 micron, and what is shown here is the FMR profile for the film as a function of the electric field applied to a bilayer of this film with PM and PT. So, you see that the shift that can be accomplished with the electric field is rather small, and the line width, the FMR line width, if you calculate the field separation between the peak and the dip here, that is more like 500 Oersted. And the tunability for this range of electric field is only 260. It is only 1/2 of the line width, just to demonstrate that this is not something you would like to use for any tunable device applications. And this is on PC and PT, and the film on PM and PT, it was rather poor tunability compared to this. But PC and PT has a much higher piezoelectric coefficient compared to PM and PT, but in spite of that, this tuning is no good as far as the device application is concerned. Now, this is zinc to Y, it is Y type hexagonal ferrite bonded to PM and PT, and this can work at much higher frequency as high as 24 gigahertz, and in this case we are able to achieve tuning by about 25 Oersted, and so it has the right characteristics for devices operating at a much higher frequency than what the frequency range one would use for EEG based devices. So, this is eclectic bonding zinc to Y, PM and PT. It shows the tuning of the ferromagnetic resonance under an electric field from 0 to 8 kilovolts per centimeter, and so the converse magnetoelectric coefficient for this system is 10 times higher than what we saw for EEG. It is close to 10 Oersted centimeter per kilovolt. So, these are two different cases, eclectic bonded and epoxy bonded. In this particular case, we found that the eclectic bonding was preferable compared to this one. So, when we go to higher frequencies, about like 50 gigahertz or more, what you would like to use is barium hexaferrite or strontium ferrite. The reason is that they have very high uniaxial anisotropy field. So, the external field that you have to apply for ferromagnetic resonance is not that high. If I want to use EEG at this frequency range, you have to apply a field of 20 or 25 kilohertz. That is rather high, whereas with this kind of uniaxial magnetocrystalline anisotropy, all you need is maybe 3 or 4 kilohertz. Okay. So, these are ferromagnetic resonance in a film of aluminum substituted barium hexaferrite. The aluminum substitution is very strange. Aluminum is non-magnetic. So, what happens is the uniaxial anisotropy field is the ratio of the anisotropic constant divided by the magnetization. When you substitute aluminum, both the anisotropic constant and the magnetization would decrease, but the catch here is that the magnetization decreases much faster than the anisotropic constant. So, you essentially you can increase the anisotropy field just by substituting aluminum, and that is what we found out. This the figure here at the bottom, it shows the anisotropy field as a function of aluminum substitution, and for 0 aluminum it is around 18 kilohertz, and with aluminum substitution you see a dramatic increase in the anisotropy field, and you can reach a value of around 34 kilohertz for aluminum substitution by 2. So, it would allow you to increase the device operating frequency just by substituting aluminum without having to apply higher and higher bias magnetic field. And in this case, what is shown here is the ferromagnetic resonance profile for a series of bias magnetic field. So, as you see here, the frequency where the FMR comes in, it increases from 47 all the way up to 59 when you increase the bias field from 4 to 8 kilohertz. So, these are the frequency versus magnetic field for series of aluminum substitution. As you see here, you can reach a frequency as high as 110 gigahertz with this aluminum substitution. So, there are devices operating at this frequency that are used for satellite communication. So, the hexagonal ferrite based devices are very useful for this kind of frequency range. So, when you go to 50 gigahertz or more, we cannot use a strip line. Instead, we have to use a waveguide for the devices, and that is shown here. This is a waveguide short, and the barium ferrite bonded to PZT, it forms the block here. So the bilayer is placed at the open end of this short, and then you excite this with microwave power from a vector network analyzer, and this is the FMR profile for the resonance in barium ferrite for a series of electric fields. It's rather small tunability, it's about 10 megahertz for a field of 10 kilovolt per centimeter, but it's extremely very high Q value for the resonance. It's close to 50,000. So the figure of merit is still reasonably good. It's the figure of merit is 30. That's not so bad. Okay. This is the same device, and so this one is pure barium ferrite, and this case is with aluminum substitution, and the FMR is seen at 106 gigahertz, and the tunability is by 3 megahertz for 1 kilovolt per centimeter of electric field. Okay, this is what I call a band pass filter. In this device based on YIG PCT, there are two microstrips. One is at the input, one at the output. The sample is placed in such a way that it lies across these two microstrips. So what happens is when you excite this with microwave power, there will not be any power transmitted to the output until you reach ferromagnetic resonance in YIG. So under that condition, the magnetic film will absorb microwave power, and it will ultimately transmit that power to the output. So it's like a filter. It allows only a certain range of microwave power with particular frequency will pass through. So it's a band pass filter, and that's shown here in this profile. The profile shows the transmitted power versus frequency for a constant bias magnetic field. So you satisfy the ferromagnetic resonance condition at 6.65 gigahertz. Then you apply an electric field across PCT. It moves the whole entire pass band from 6.65 to 6.725. Then you increase the electric field further. So the pass band is shifted to higher and higher frequency as the electric field is increased. So that is tuning the operating frequency of this filter. Okay? So you can tune it by as much as 125 megahertz for a field of around 2.5 kilovolt per centimeter. And the figure of merit for the band pass filter is the figure of merit for the resonator divided by the insertion loss. What is the insertion loss? Look at the number here. The power transmitted at resonance is around minus 4 dB. That means if there are no losses, you have to have this peak right at 0 dB, whereas it's not at 0, it's at minus 4. So there are losses in all of these parts. There is a loss in the microstrip that carries the microwave power, and also there are losses in the yttrium and garnet. These are magnetic losses. There are losses in the ferroelectric. So that combines together to give rise to an insertion loss of 4 dB in this particular case, and you want to keep it as small as possible. So this is the same device. Right. So, you can put together a dual resonator filter where there are 3 microstrips, one at the input, then one there is an intermediate one, then there is an output. Then instead of only one EPCT, you have 2 of these elements. The idea is when you have a dual resonator filter, you can have a pass band which is rather flat but wide. So, if you want the filter to work over a wide frequency range, so you have to increase the number of resonators from 1, 2 and 3. So, that is what is shown in this particular case. And phase shifters, they are used in phased array radars. So, in phased array radars, like for example, if you want to scan the sky for any object, then you have to direct the beam in a particular direction, and you can scan the beam over a wide angle. So, the phased array radars have phase shifters that would allow the beam to be directed or scanned over a certain angle, and YIG PCT can be used for that kind of application. And but I don't want to spend too much time. We are running pretty close to my time limit. So, with YIG PCT, you can apply an electric field and change the phase and then do the scanning with this kind of device. So, I can put together a similar phase shifter operating at much higher frequency from 10 to 24 gigahertz with a bilayer of zinc 2Y and PM and PT. And these are phase shifters operating at 50 gigahertz using barium hexaferrite. So, what is a delay line? When at the receiving end of a radar, you have microwaves coming in. So, you can have the resonator pick those frequency band, but ultimately you want to have the selectivity for a particular frequency. So, that is where the delay lines come in. So, as the waves come in and propagate through the YIG, so you can separate them in time domain using this delay line. So, it will convert the signal from the frequency domain into time domain, so that it will be received at certain time intervals, and that is what is shown here, the time delay over a certain frequency range. These are not ferromagnetic resonance, they are called magnetostatic surface waves. So, just take it for granted that they come in and you have the waves over a certain frequency range, and when you apply an electric field, the time it takes to propagate through the YIG film can be controlled. So, as you see here, you have the control with an electric field. Under 0 electric field, the time delay will be around 200 nanoseconds. When you apply an electric field of 8 kilovolts per centimeter, it comes down to 100 for this particular frequency. So, that is how these can be useful. And attenuator are used if the incoming power is too high and you do not want to expose the circuit elements to such high power, because they can just literally burn them up. So, attenuators are used to decrease the incoming power in a device, and that can be done with YIG, PM and PT, and that will give you the ability to control the attenuation. These are based on ferromagnetic resonance in YIG. By applying an electric field, you can tune the ferromagnetic resonance, and that way you can tune the attenuation. If you are sitting at particular frequency, for example 7.24, you see here the profiles, as you go parallel to this frequency along this axis, here the attenuation is minus 15, then it goes to minus 10, -3 and -1. So that's the way you can change the attenuation for the incoming microwave frequencies by changing the electric field. So the hybrid wave devices, they are based on that it's a combination of the dielectric resonance in the ferroelectric. In this particular case, it's a platelet of bismuth strontium barium strontium titanate. Then you have magnetic resonance in YAG. You combine the two resonances to make hybrid waves, and they are tuned with an electric field or a voltage. It's ranging from 0 to 800 volts. The tuning that's shown here is by close to 400 megahertz. Okay, then so this is a hybrid wave device, but the only problem here is they are much higher in terms of losses compared to FMR based devices. So it's a phase shifter based on hybrid waves. All right, to summarize, I talked about dual tunable high frequency devices. If you want to change the operating frequency, and if you have the ability to apply a variable bias magnetic field with the use of either a solenoid or you can use a permanent magnet, then you should be able to tune the position of the magnet in and out with some kind of a mechanical tuning. If you can do that, then you can tune the frequency also. But with a permanent magnet, the field that you apply to the film is non-uniform. That can lead to a spread in the FMR profile. So instead of 1 R-stud for the E line width, you may get 10 R-stud because of the non-uniform magnetic field. But if you can live with it, then you don't need any PCT or you don't need any voltage source. All you have to do is tune the magnet mechanically and you should be able to get it. And so we also looked at voltage tuning of resonators, filters, both passband and stop band filters, phase shifters, delay lines, and attenuators. So the advantage here is with voltage tuning, it's passive. That means it requires very little power. PCT has a very high resistance, and when you apply voltage, there is very little current. So the overall power consumed by the tuning mechanism is extremely small, just few milliwatts or microwatt. So these can be miniaturized very easily, and also you can integrate them with any semiconductor device, and you can put together the whole circuit on a circuit board, whereas that's not possible if you go for magnetic field tuning. And they are quite useful. And also we are working on how you can enhance the tunability over several bands. That's something that may occur in the future, but at this time the tuning range is very small, and it can be useful if you want to compensate for any change in the temperature of the operating device of these signal processing components. Otherwise, you cannot imagine having the tuning from X band to K band to millimeter wave frequencies. That's not what we are talking about. So limited range, but very power efficient, and it's still useful for many applications. Okay. All right, thank you. Any questions? Yeah, that's very critical, because when I talk about EEG based devices, if you have power more than a few milliwatt, then there are called, what are called spin wave instability. It can create a real problem for the device to operate, and you have what is called high power effects. It can lead to secondary absorptions and also excessive heating of ink film, and it will stop operating. So, it is very, very important to make sure that the power under which these devices operate is not more than few milliwatt. If you go up to 100 milliwatt of microwave power, everything falls apart. Yeah, that is a good point. Yeah, you are right.
Most of the devices, dimension plays a very important role. Assuming that you are using the ferromagnetic resonance, the waves that are generated within the material, if we control the dimension of the material, will there be any other improvement in that? Because there may be a standing wave formed within the material due to the spin waves.
Yeah, so most of these devices, the ink film is very tiny, maybe like 1 millimeter wide and few millimeter in length, because in case if you are applying an in-plane field, you want to make sure that the demagnetizing factor is small. Okay. So, thin film, long and not so wide. But apart from that, if you have a very large dimension for the ink film, then you tend to excite several standing wave modes. So, there are series of standing wave modes, and instead of one single FMR, you may end up with a fine structure spread over a certain frequency. So, the frequency selectivity may go bad if the film is very long. But what is the limit? That is something one has to be careful, but it is just by trial and error. We can make devices with different lengths for the ink film and probably come up with the optimum dimensions for it. All right.